Okay, so question 5 part B involves the following. So you're asked what happens if you treat this molecule here with S-butyl, so S-butyl lithium. And what I'm expecting you to recognize here is that S-butyl is a really strong base, so anytime you see butyl lithium, you think it's either going to deprotonate something or maybe it'll do a lithium halogen exchange, but there's no halogens in this molecule here, so you think it's going to deprotonate something. And this is an example of ortholithiation, or deprotonation next to a directing group. So this is going to direct the deprotonation to this site here. So either of these protons, they're both orthoprotons, one of them is going to get deprotonated, and when it does, the base is going to come along, take that hydrogen and leave a negative charge on the carbon. So rules haven't changed. Try out everything exactly the way it was, except for what you've changed. So that hydrogen there has now transferred over to our base, and this negative charge here is now because there's a carbon lithium bond there. So that's the first piece. What happens next? Well, in the next part we introduce benzaldehyde. So this molecule here. And what I'm expecting you to recognize here is that carbons or carbon lithium compounds are strongly nucleophilic. So whenever you see them, they will act as bases, but if there are no protons to be deprotonated and there are no halogens to exchange with, they will act as nucleophiles in exactly the same way that Grignard reagents will act as nucleophiles. This carbon with a negative charge is very strongly nucleophilic, and you have to identify the electrophile in what we've just added. So we've just added benzaldehyde, we add in, this is our electrophile, the carbonyl carbon is obviously the electrophile, it's going to attack here, so you can redraw it if you want, or you can draw it attacking there and making a tetrahedral, not intermediate in this case, but a tetrahedral final product. So what's that going to look like? Well, let's try draw out everything exactly as it was. Made a new carbon-carbon bond from there. Negative charge now on the oxygen. There was a hydrogen attached to that, and there was also a benzene ring attached to that. And that's it. That's the answer to that part of the question. Full marks. If you were doing this in real world, you'd also put in a little bit of acid when the reaction was finished so that you got the alcohol back. If you draw on the alcohol, you can have the marks for that either. But that's the first part. So, staying with the theme of treating compounds with butyl lithium, the second part of this question asks what happens if you take a similar related compound. So if you take this same compound except with a bromine in the para position and you treat that with this time 2 equivalents of tert-butyl lithium. So this time what's going to happen? Well, this time I'm expecting you to realize that, yep, tert-butyl lithium is a very strong base, but it'll also do lithium halogen exchange, and it will do lithium halogen exchange much faster than it will deprotonate, especially if there's no activating TMEDA in there. So lithium halogen exchange much faster than deprotonation in this case. So what happens when we do lithium halogen exchange? Well, the lithium, the halogen will exchange, so this will attack the bromine and kick out the much more stable carboanion or carbanion. And you make a carbon lithium bond. You can draw that out as the negative charge and the positive charge if you want. And you also have your tert-butyl or suppose 2-bromo 2-methyl propane. And you still have a second equivalent of butyl lithium in there, and the reason that that's in there is to prevent the reverse reaction. So it will very quickly eliminate out the bromine or the hydrogen bromide across this. So if we put that in, it'll act as a strong base. It will take this proton, form the double bond, kick out the bromide, and what you'll be left with is your lithium compound, which is what you wanted. You can go on and do whatever reaction you want, and you will also be left with 2-methyl propene and 2-methyl propane and lithium bromide. So that's that reaction. You can see the only difference here is that there is a halogen. So when you see your butyl lithium compound, you need to inspect the molecule it's going to react with carefully and decide, is it acting as a base or is it acting as something to do lithium halogen exchange. And the equilibrium of this reaction is always going to be driven towards the much more stable anion, the much more stable carbon lithium compound, but it's also forced to completion because this reaction here is irreversible. You're making a lithium bromide salt and 2 stable alkene and alkane. So that reaction will go essentially to completion. Okay, and then the very last part of this question, you're asked to describe what happens if you treat phenyllithium, so our carbon lithium compound has been generated in advance. What happens if you treat it with 1,2-dibromoethane? And the answer to this is that initially you get lithium halogen exchange. And you get these two compounds here. But as you know, the equilibrium, if this is all that was going on, would be far in favor of this compound here, because the pKa of this might be a billion times, this might be a billion times more acidic than this hydrogen here. So why does the reaction go this way? Well, this lithium bromide compound, the same as what's happening here, isn't going to be stable, and this is going to eliminate almost instantaneously to give you lithium bromide and ethene, and that is irreversible. So even if only a small amount of this is there in equilibrium with this material here, as soon as this is generated, one of the products is eliminated, and if we eliminate out one of the products, Le Chatelier's principle says that the reaction is going to keep driving to make more of it, and so the reaction goes to completion. So there were 8 marks going for that question. There are 1, 2, 3, 4 things that you had to, or products that you had to find. What I'm trying to get at here in this question, the reason I wrote it the way I wrote it, is that I want you to be able to recognize both lithium halogen exchange, which we covered, and also, lithium halogen exchange and ortholithiation, because they are related but not identical, and to know that lithium halogen exchange happens faster than ortholithiation. And then this last bit was just a little bit of a challenge to see, could you figure out this was going to go against the equilibrium. But we've also seen that as an example in lectures. Okay, if you have any questions, post them below or ask me on Teams or something like that.